third lecture on the solution of wave equation. We shall consider the wave equation in 2D. Firstly, we shall consider the vibration and apply the theory to the vibration of membrane. Firstly, we shall consider a rectangular membrane. A rectangular membrane in XY system. This is the X coordinate, Y coordinate, and we assume the membrane to lie between X is equal to 0 to A and from Y is equal to 0 to B, and the membrane is fixed at its rims. So the solution, the transverse vibration that is set up in this motion in this membrane is governed by the two-dimensional wave equation. The special part, it is governed by 2D equation. The special part is given by special part of wave equation. Wave equation is the Helmholtz equation. For 2D Cartesian system, 2D Cartesian coordinates, the Helmholtz equation is del 2 del x2 plus del 2 del y2 plus k square of phi of xy is equal to 0. Assuming separation of variable technique, we choose phi of xy is equal to x of x into y of y. Recall that the time part is already obtained. T is equal to A cos omega t plus B sin omega t, where omega is equal to V into K. And if we substitute this here for non-trivial solution, we get 1 by x d2x dx2 plus 1 by y d2y dy2 plus k square is equal to 0. If we take this part on the left, so we get this is equal to minus k square, and this must be equal to a separation constant is equal to kx square, where periodicity of x solution demands that kx has to be a real quantity. So we have for x solution now, since this membrane is stretched is fixed at its rims, we assume the solution in the form of stationary waves. So we write it C sin kxx plus D cos kxx, and the y equation now becomes d2y dy2 is equal to plus k square minus kx square y is equal to 0. We set it as ky square. So we have d2y dy2 plus ky square y is equal to 0, where k square is equal to kx square plus ky square. note the change in connection with the corresponding case in Laplace equation. For Laplace equation, we found that if we have periodic sinusoidal solution in one component, then the y component has to be exponential or vice versa. But for Helmholtz equation, we can have, or we do have, sinusoidal solution for both x and y direction. And again, y of y in the form of stationary waves is e sine ky y plus f cos ky y. These are the solution. Now what are the boundary condition of the problem? The boundary condition is that conditions are u at x is equal to 0, at y all values of y t is equal to 0 is equal to u at x is equal to a y t. This in terms of x becomes x is equal at, if we consider this case, this part gives you d is equal to 0, and this part gives you kxa is equal to n pi, or kx is now quantized, kxn is equal to n pi by a. Similarly, we have another boundary condition, but this is boundary condition 1. The boundary condition 2 is u of x0 t is equal to 0 is equal to u at x b t. This in terms of y becomes y at 0 is equal to 0 is equal to y at b. This part gives f is equal to 0, and this part gives kyb is equal to m pi. So ky is now quantized, kym is equal to m pi by b. Now coming to k values. K value, actually it is kx plus ky, so so far its magnitude is concerned, k square is equal to kx square plus ky square. So we call knm square is equal to pi square n square by s square plus m square by b square. So coming to omega is now depend on nm and is equal to v times knm. This is equal to pi v n square by s square plus m square by b square. So this is the omega. Now we see that this solution doesn't have this part and this solution doesn't have this part. So this is a constant, we can adjust the final constant to define unm of x, y, t. This is xn of x, ym of y, t and m of t. And we write it as, these constants are changed, so this is anm cos of omega nm t plus b and m sine of omega n m t, this is the temporal part, multiplied by sine of n pi x by a sine of m pi y by b. This is the solution for a given pair of nm. The general solution is u of x y t is a summation over n and m ranging from 1 to infinity, u of n m x y and t. So this is summation over n m 1 to infinity a n m b n m sine of omega n m t sine of n pi x by a sine of m pi y by b. This is the harmonic solution or the most general solution. So if we solve the second or two-dimensional wave equation for a rectangular membrane, we'll end up with this to be the solution. Here, in arriving at the solution, we have used two boundary conditions. So the solution, final solution is this. We just write the final outcome of the solution. U of xt xyt is equal to summation over n m 1 to infinity a n m cos of omega n m t plus b n m sine of omega n m t sine of n pi x by a sine of m pi y by b, where omega n m is defined as pi v n square by a square plus m square by b square. For a square membrane, A is equal to V. Now, and we know the velocity. We know the velocity. Velocity is xyt is del u del t. If we differentiate this expression, we get this is summation over nm from 1 to infinity. Omega nm comes out, and this is minus a nm sine of omega nmt plus b nm cos of omega nmt multiplied by sine of n pi x by a sine of m pi y by b. This is the expression for velocity amplitude, and this is the expression for velocity. The initial conditions are generally supplied as the initial displacement and initial velocity. So we call u0 of xy as u at xy0. So from this equation we get this is summation over nm 1 to infinity. It is anm sine of n pi x a sine of m pi y by b, and the initial velocity is v0 of xy is equal to v at xy t is equal to 0. If we come to this equation, this is y by b. This looks like just double Fourier transform. If we multiply both the sides of this equation with sine of n prime pi x by a and sine of m prime pi y by b and integrate it over x is equal to 0 to a and y is equal to 0 to b, we get a n prime m prime is equal to 4 by ab times u0 of xy, integration dx from 0 to a, integration dy from 0 to b, u0 xy sine of n prime pi x by a sine of m prime pi y by b, and this gives you b and m. Similarly, this gives you dy from 0 to b, v0 of xy these are the expressions for a and b. Now a particular mode of oscillation, that is u and m, is determined by two numbers n and m. We say the nm mode is as represented by u n or phi n m x y, and we want to see what happens to this case. So nm mode means the special part is given by this equation. Recall that phi nm xy is apart from constant, it is sine of n pi x by a sine of m pi y by b. So we see this part for a given value of n, it has zeros at x is equal to 0 and a. For n is equal to 1, it doesn't have. For n is equal to 1, the solution is like this. Sorry. For n is equal to 1, solution is this. For n is equal to 2, the solution is like this. This is n is equal to 2. If we choose this direction, this is m is equal to 1, this is m is equal to 2 in y direction. We'll see that for n is equal to 1, entire membrane along the x direction has either positive displacement or negative displacement. Similarly, for m is equal to 1, entire membrane along y direction has the same displacement, that is, they are all in phase. While for n is equal to 2, the entire membrane along x direction is divided into two halves. First half, if the first half is in phase, then the second half is out of phase with respect to the first one, and there is a line along which there is no displacement, so we have a nodal line. Similar thing happens here. So we can divide the membrane in along nodal lines, as we have done in case of vibrating string. We got the nodal points. Here we say this is the membrane. So for 1-1 mode, entire thing is in phase. Now we consider the 2-1 mode. So along x direction, it is divided into two parts. This first half vibrates in phase. This is a nodal line. This part vibrates out of phase. So now come to 3-1 mode. This entire strip is divided into three equal halves. This part vibrates. These two, if all the points of this half has positive displacement, then it has negative displacement, this again positive displacement, and along the line there is no displacement, that is the nodal lines. Now we come to 2-1 mode, 1-2 mode. 1-2 mode, along y direction, this is the for 1-3 mode. And we are considering 2-3 modes. So we consider 2-3 mode. It is along x direction, it is divided into two parts because it is 2-3 mode. Along y direction, we have divided into three equal parts. This is the situation, these are the nodal lines, and still we can draw the nodal planes for still higher order, higher modes of vibration. So this is all about the vibration of a rectangular membrane. As the second example of vibrating membrane, we consider the vibration of circular membrane. We assume a circle in xy plane centered at the origin and it has a radius a. This is xy plane. This is a membrane in xy plane, and we choose the coordinate system so that the membrane lies in xy plane, and the center of the membrane is the origin of the coordinate system. So this is the origin of the coordinate system, and the transverse vibration is governed by the Helmholtz equation. Due to this symmetry, we use the polar coordinates r theta. So the special part is governed by Helmholtz equation, which is psi of r theta is equal to 0. Now this is 1 by r del del r of r del del r plus this is the Laplacian in polar coordinates. This is the Laplacian in polar coordinates plus k square, we put it within second bracket, plus k square. This is the entire operator, and for this we use the part r of r and big theta of theta is equal to 0. That is, we set r theta is equal to big R of r times big theta of theta. This becomes, we operate this on, so this is 1 upon small r by capital R, then ddr of r dr plus 1 by r square big theta d2 big theta d theta 2 plus k square is equal to 0. Here we have used this, and for non-trivial solution we have divided all through by big R big theta. So this is the solution. We separate out the theta part from the rest. To separate out theta part, we multiply entire thing by r square, and we get r by capital R ddr of r dr plus k square r square is equal to minus 1 by big theta d2 big theta d theta 2. You see, the left hand side is a function of r only and right hand side is a function of theta only, and we set it as n square so that the theta equation becomes so the theta equation is theta of obviously n is an integer. Obviously n belongs to integer. Otherwise the periodicity condition has to be satisfied, will not be satisfied. N of theta is equal to theta n of theta plus 2 pi, which indicates that n has to be an integer. Now, having n being an integer, this equation comes out to be r square d2r dr2 plus r dr plus k square r square minus n square r is equal to 0. This is the Bessel differential equation, and the solution is r of r is Cn Jn of kr plus Dn Na Yn of kr, where it is the Bessel function of first kind and it is the Bessel function of second kind. The membrane extends from r is equal to 0 to infinity. Since this has a divergence, Yn has a divergence at r is equal to 0, so we set d0, dn is equal to 0, so this is Cn Jn of kr. So for a particular n, we have, for a given n, and we have the solution. This is the Laplace's Helmholtz equations. Is phi n of r theta is equal to r n of r times theta n of theta. This is equal to Cn, and these constants are adjusted accordingly. So we call it An cos of n theta plus Bn sine of n theta multiplied by Jn of Kr. And n can have values from 0 onwards, so the most general, and this is the solution. And for time part, we have to multiply it. For time part, the general solution is un r theta t is equal to psi n of r theta times t of t, and Tn, you see that Tn is obtained in terms of omega. So this is equal to An cos of n theta plus Bn sine of n theta Jn Kr plus, this is called A, this is A cos omega t plus B sine omega t. This is the solution for a particular n, and the general solution is the superposition of all solutions r theta t is equal to summation over n is equal to 0 onwards. Here n is equal to 0 is included, u of n r theta t. So this is summation over n. Now the boundary condition. Boundary condition is that u of a theta t is equal to 0 always. That is the circular membrane is fixed along its rim, so the displacement is 0 over the circumference of the ring, and for all values of theta t. So that indicates that Jn of K A has to be 0, and this is called this is Jn of lambda nm. These are the lambda nm. Lambda nm is the mth 0 of Jnx. So we see that K is now quantized. So K is now become K of nm is equal to lambda nm by A. So since K is quantized, Although not as simple as we obtained in the case of rectangular membrane, still it is quantized. Since k is quantized, omega has also quantized values. At first sight, it appeared that appeared foolish to include omega within the summation sign, but the reason is that since k will come out to have quantized values given by the zeros of Bessel function of integral order, consequently omega n will also be quantized. So we rewrite this solution as, and correspondingly correspondingly omega now becomes omega nm, which is v times knm, that is v times lambda nm by a. This is the omega values, and this solution now becomes u of r theta t is equal to summation over n is equal to 0 to infinity and the zeros of Bessel function 1 to infinity. Then all these constants will have nm's signature. nmt plus b nm sine of omega nmt times, this part will also have nm signature, because this is an cos of n theta bn sine of n theta times jn. Now k is replaced by knm, so this is knm. For knm we write lambda nm x by a. This is the solution. There is one other thing appears for symmetric vibration. A symmetric vibration for symmetric mode of vibration. U is a function of RT that indicates that the solution has no theta dependence. Since the solution doesn't have any theta dependence in symmetric mode, n has to be 0. This lets n is equal to 0, in which case it will be J0 and there will be no sum over n, and the solution will be URT is equal to summation over n is equal to 1 to infinity, and there will be no n term. So this is an cos of omega 0 mt plus bm sine of 0 mt times j0 lambda 0 m x by a, where lambda 0 m is the mth 0 of j0 of x. This is known as the symmetric vibration, symmetric modes of vibration. That's all about the solution of wave equation using the separation of variable techniques.